Now, so far we've looked at one variable in the averages chart or two variables in the scatter plot. Now we're moving to three variables. And we're still going to use the scatter plot, but we're going to add a third dimension, so to speak, by changing the size of the point. So in the original scatter plot, all the points have the same size. X variable, Y variable, you have points. Now we're going to change the size and the color of the points as a function of a third variable. So what's the question? Again, it shouldn't matter, right? And it shouldn't matter translates in that the bubbles of all sizes should be mixed together randomly. But if all the small bubbles are in one corner and all the large bubbles are in another corner, that suggests an interaction between the three variables. Remember, bivariate correlation can be very misleading if it really works through a third variable. And that's where multivariate analysis comes in. So multivariate analysis, tries to control for these interactions. Here we're not controlling for it, here we're checking for it. The point of departure is there shouldn't be any interaction. If we see meaningful patterns of these bubbles in the bubble chart, then we might have interaction. And then we definitely should not trust the pure bivariate correlation. We have to go the multivariate route, okay? So let me look at my cheat sheet here. Bubble chart is here. And there's a lot of things you can pick. We're going to make the bubble size and the bubble color the same. If you really have good visual perception, you can make them different. And then you have four variables. One for X, one for Y, one for the bubble size, and one for the bubble color. I don't recommend it. Okay? Colors can be very misleading. But if you're good at this stuff, by all means. So X variable is percent population with an educational gap. That's P Duc 20. And the Y variable is P serve 20. Where is this? Here. The percent population without access to basic services. And the bubble size and bubble color are our PPOV again, which is not PPOV, but this one, PPOV 20, and here PPOV 20. Okay. So what do we have here? X and Y, just as before, but now we're changing the size of the dots in the scatter plot as a function of this third variable. If you do okay, it doesn't look that great, right? But, and it almost never looks fine the first time. But if you right click, go down here, adjust the bubble size, and this will look different depending on your computer. You shrink the bubbles a bit, then we have a nice graph. What's interesting about this graph? So the color scheme is a standard deviation scheme. Low are small values, high are big values. And the size, same thing. Big size is high extreme poverty, small size is doing well, right? Remember what I said, the point of departure is that the bubble size doesn't matter. Does it matter here? Yes. All the bigger bubbles are near the top and the right-hand top corner. All the teeny bubbles are near the low right-hand, this kind, left size. Okay. So that shouldn't happen, right? It's not because you see it that you say, oh yeah, it's always like this. No, it's by no means always like this. I had to work long and hard to find one where this is like this, right? if you do this with a random set of 3 variables, it's probably not going to be like this, right? But this is an instance where there is a strong suggestion of interaction, even though we're only working in 2 dimensions. Why? Because we bring in the 3rd dimension through another device. The size of the bubble and or the color of the bubble. So in a sense, we're cheating, but that is what all these methods are about. We only have a screen, we only have 2 dimensions. How do we get insight into higher dimensions in only 2 dimensions? And this is one way of doing it. Another way of doing it is a conditional plot. And a conditional plot has a lot of different names in different literatures. It was originally developed at Bell Labs and was called a trellis graph. But trellis graph is trademarked, so nobody else can use it unless you pay AT&T some money. Then clever people came up with other names for it, which is exactly the same thing. Small multiples in ggplot, which is a big graphics package in R. It's called facet graphs. It's all the same thing. What is the idea? Again, higher dimensions into 2 dimensions. So we have any kind of statistical graph, let's say a scatter plot. Let's say the scatter plot between education and food, the same thing again, right? Now, if we bring in another variable and we make the scatter plot for subsets of values of the other variable, let's say low values and high values. If there is no interaction, then the 2 scatter plots should be exactly the same. If there is interaction, then maybe one is positive and the other one is negative, or something like that. Or the other one is flat, so there's no relation. So anytime you see these microplots, they're called microplots or micromaps. If you can do this with maps too, I won't get into that today. Anytime you see them showing a different pattern, then you should say, hey, this shouldn't happen. If there is no interaction between these variables, remember, we're in a multivariate world now. It's not just 2 variables, it's multiple variables. And are the relations between 2 variables may be influenced by a 3rd variable, so that one of these could be a proxy for the 3rd one. And you really want to control for that in the end. And you can go even further. You can condition on the vertical axis as well. And so then you have 4-dimensional interaction reflected on a 2-dimensional graph. Okay, let's see what this looks like. So I'm going to get rid of my the conditional plots are all here. There's actually 4 different kinds. You can do this for a map, you can do this for a histogram, for a scatter plot, and for a box plot. I'm just going to show the scatter plot and the box plot. So the scatter plot first, and there's 4 things to pick. The easiest ones are just the scatter plot variables, and we're going to take X is this education variable, and Y is the food variable, this one, okay? And the first condition on the horizontal side, it's a hard one to find, is population change between 2010 and 2020, and it's below. I always have a hard time finding it. I probably should have picked a different variable. It's after p dot 20. So you see they're all the same. 00 is for 2000. Then 10 is for 2010. You see there's a lot of variables. And they're both in counts and in percentages. Here we're in 10. Here we're all in 10. You just keep going, keep going. Pretty soon we're going to be in 20. Here we go in 20. It's this one. So that's the population change between 2010 and 2020. It's actually a dummy variable. It is 1 if there is growth, and if 0 if there's no growth. So that's our first conditioning variable. And the second additional variable is our old friend altitude. So that's easy to find. That's very much near the top. There's altitude. So now the horizontal axis is population change. The vertical axis is altitude. And then we have different microplots. So what is going on here? We take the observations that fall in the particular conditioning category. So no growth, growth, right? Low altitude, middle altitude, high altitude. So let's say growth, high altitude. You take those observations and you make a scatter plot just for those observations. So for each of these boxes in the conditioning plot, you make one of these mini plots. And again, just like with the bubble chart, these mini plots should all be the same. If they're not the same, then it suggests an interaction between one or both of the conditioning variables, right? So let's see what this looks like initially, and it looks really weird, right? And why does it look weird? Because it assumes that the conditioning variables are continuous, and they're not. This is remedied by looking at the options, and you can control the brakes for the vertical bins and the horizontal bins. So the horizontal bin, we know it's 0 and 1, so we're going to change it into unique values. And the moment we do this, the graph will be adjusted. So if you go to horizontal bin brake, unique values, now we're in business. We have no growth, we have growth, we have low altitude, middle altitude, high altitude. So what do we see? These two pretty much the same, these two pretty much the same, these two are different. So there is some suggestion that for the middle altitude places, the relationship between these two variables is different. Again, that could suggest a form of interaction. It definitely suggests a form of heterogeneity, and that is what you further investigate. You can do this, I said, for 4 different plots. Let's take a different variable, and we're going to make a conditional box plot for different variable. Let's see. The horizontal cell is region. It's a lot easier to find. It's right on the top here. Remember, region is a number. 1, 2, 3, 4, I think there's 9 of them. Vertical cells, nothing. Click on the blank. And then the variable is, I think this one here. % lack of access to healthcare. In the average plot, we had selected and unselected. Here we have selection, but on multiple categories. So if you say okay, again, initially, you say this doesn't make any sense, you know? This value is 3.5, this value is 7.5. The regions are discrete codes. Again, it's the same problem. We go and we do horizontal bin breaks. We make them unique values. And then you have a separate box plot for each region. And this is an alternative to a much more powerful alternative to the averages chart, because not only can you visually assess whether these medians are the same, and for example, this one, where is our region 8? Yeah, these is our central valleys and lack of access to healthcare. So this is much higher than, say, this region here. And then, of course, you can always brush and link, and we go to the map. This is where these areas are. And similarly, but not that meaningfully, you can brush the other way. So this is another way to do a conditional plot, but conditioning on discrete variables. And one way in which this is useful is, if you remember, in one of the very first demos, when I talked about the selection tool, you could select by drilling down into the data, or you could select on the map. And then you could save your selection as an additional variable. So if you save your selection, then that becomes a way to use in a conditional plot, because you can do any plot for the selected and the unselected. And again, the point of departure would be they should be the same. If they're not the same, again, that might suggest some form of spatial heterogeneity.